Hello pre-calc. So this kind of takes me back to last year making videos. This will be not terribly long. It's just inverse functions. So I know you kind of did this probably way back in Algebra 1, so let's kind of review what is an inverse function and how you find it. So first off, finding an inverse function. The process is you are going to switch the x and the y variables in your equation, and then you will solve or isolate for y. So let's do a couple. So the first thing I would do is I would rewrite f of x as y equals, and this is x plus 6 over 2. All right, so our first step is to switch the x and the y. So I have x equals y plus 6 over 2. And now my goal through order of operations is to isolate y. So the first thing I'm going to do is multiply both sides by 2. And next, then we're going to subtract 6. And voila, we have what we would now call the inverse function. And in this case, actually, I'm running out of space right there, aren't I? So let me do this the other direction. So we would then rewrite this as the inverse of f of x, because we don't want to just call it y, because we already have y equals x plus 6 over 2. We want to somehow distinguish them and show that they are related by an inverse relationship. And we'll talk about what that is in a second. But let's do one more. So we are going to, again, take a little shortcut and call that y. And so the first step we do is we switch our x and our y. So this becomes x equals 1/2 y squared plus 2. And again, our goal is to isolate y, so I'm going to have x minus 2, so I'm going to do our order of operations, equals 1/2 y squared. Then we will multiply this side by 2, so this all goes into parentheses. And then when I go to take the square root of both sides, I have to put a plus or minus in front of this, and that will then equal my y. And as you will see in a minute, so this is going to be, I'm going to call it y prime. I'm not going to call it y inverse, because that, oh, I lost my radical when I did that, plus or minus the square root. Sorry about that. Because this is not going to be a function if I graphed it, because it would be a sideways parabola, it's not going to get the inverse function. So because this isn't, the inverse is not a function, it would not pass the vertical line test, it doesn't get the privilege of being called f inverse. It's still an inverse, in this case we guess we'd call it an inverse relation. Now, what is the relationship in terms of graphs? Well, we switched the x and the y, so there's a big clue there. Your inverse functions are reflections over the line y equals x. And we're going to show why this is so for the ones that we just did. So we're going to graph what we did up above. So our first function we had was y equals 1/2. I'm going to write it like this. Then this would be x plus 6, but if you're going to graph it, that would simplify to 1/2 x plus 3. All right, so that was our very first function. So we're going to go up to 3. We have a slope of 1/2, up 1 over 2, up 1 over 2. Let's see if I can, down 1, back 2, try and draw a straight line through that. All right, so there's that function. Its inverse that we found was, where is it? 2x minus 6 Oh, my cat is very noisy, sorry about that. So here's -6, up 2 over 1, up 2 over 1, and you know what? I'm going to keep going. 2 over 1, 2 over 1, because look at that, we're right on the graph. And I'm going to draw a straight line through those. Now, to kind of represent, it's hard to use, I can't use a ruler on an iPad, it's kind of hard. But I'm going to now draw the line y equals x, so you can kind of see, hopefully I can draw this straight, that they are reflections over that line. So when you're trying to find an inverse and you don't have the function, you can just switch the x, y coordinates, and that would be another way to graph an inverse function. Okay, let's take a look at the second one. The second one, we had y equals 1/2 x squared plus 2. So you're graphing a parabola that is dilated by 1/2 and translated up by 2. So the vertex will be here, and instead of over 1 up 1, you would go over 1 up 1/2. And instead of over 2 up 4, we're going to go over 2 up 2. I think I got that close enough for what we're doing. So that would be that original function. And then our inverse relation that I called y prime plus or minus, what is this, 2x minus 4. Okay, so here is where it's really helpful. I'm going to draw my y equals x, there's that. So we know this is a reflection. And I'm like, plus or minus radical 2x minus 4? I have no idea. I mean, I could figure it out. I could plot it in points. But since I know it's the inverse, I just take values off of my other parabola. So this was at 0, 2, so at 2, 0. Oops, I should use a different color. I'll use green. So 2, 0 is going to be the vertex. I know that I went over 1 up 1/2, so now I go down 1 up 1/2, and then up 2, so I went up 2, forward 2, because we had that dilation in there. And voila, you can see it is a reflection over the line y equals x. So one of the nice properties of the inverse is if you don't know how to graph that inverse function, just take points off of your original and switch the x and the y. So now let's talk about this whole concept invertible. Like, why didn't, the second function get that f of inverse? Well, there's a couple things that have to be true. So if your original function, this is like a predictor. We know that you can tell the original function is a function if it passes the vertical line test, but if it also passes what we call the horizontal line test, I'm only going to write this once because it's the horizontal line test, well then that tells me its inverse is a function without actually having to find the inverse. I know that the inverse will also be 1 to 1. Another way to tell this, another predictor that the inverse will be a function or that it would pass if you, is if your f of x, your original function, is, we say monotonically, I'm just going to not use such big words, if it's always increasing or decreasing. In other words, no turnarounds. If that's true, then it would also pass the horizontal line test, which means the inverse would be a function. So if f of x is always increasing or decreasing, then its inverse is a function. And we also say, so an invertible function, meaning the inverse is 1 to 1, means the inverse, or an invertible function is 1 to 1. I should say that. An invertible function is 1-to-1. So that means f of x passes the horizontal line test, and f inverse of x passes the vertical line test. In other words, everyone's a function, okay, when it comes right down to it. If it's invertible, it's 1-to-1, which means both functions are functions, not relations. So f of x would pass the vertical line test, but it also passes the horizontal line test, which means the inverse passes the vertical line test because it's going to be a function. Visually, invertible functions, so here's some nice examples. Let me make a couple x, y axes. Here we go. All right, so you might have something like this that is always decreasing. You might have like a linear function. You might have something that looks like that. Notice it didn't turn all the way around, always going up. You might have something like that. Those are a few examples. Not invertible. Let's give ourselves a couple examples. So notice in the invertible side, all of those would pass the horizontal line test. So not invertible would be, say, a parabola, because you got to turn around there. Or we saw before, sideways parabola. Your sine and cosine graphs, those won't work. Anything that has any kind of a turnaround, that's where it's not going to pass the horizontal line test or the vertical line test. Okay? There we go. So it has to be invertible to get the privilege of being called f inverse. Now, definition of an invertible function is that if I take the composition, which we did just the other day, of the inverse, I get back x, which is equivalent to if I took the inverse on the outside. So it works both ways. It doesn't matter which way you do it. So f inverse of x equals f of f inverse. How would I show that? Well, let's do it. All right, so here we have two functions, and we want to show by composition that they are invertible. So I'm going to find f of f inverse first. So this is going to be 3 times plus 12. What goes inside is going to be the inverse, my g of x, I guess. So this will be 1/3 x minus 4. So when we distribute, we get x minus 12 plus 12, which gives us back x. That's good so far. But now let's do the f inverse, which we're calling our g of x of f. So this is going to be 1/3 with a placeholder. F goes on the inside now, 3x plus 12. So 1/3 of 3x is x plus 4 minus 4, and voila. So in both cases, we get back x, so we know those are inverses of each other. All right?